It's time for the chain rule. So back in single variable calculus, we were dealing with functions where you have y is equal to f of g of t, and if we wanted to calculate the derivative of y with respect to t, then we needed to apply the chain rule. So when we're dealing with functions of one variable, we had two ways that we could write this down. There was probably the way that we all did the chain rule and maybe feel the most comfortable with. So that's the second version. If we want to take the derivative with respect to y derivative with respect to t of y, then we take the derivative of the outer function, you plug the inner function in, and you multiply by the derivative of the inner function. Right? And so what's the other way to write this, the other way to think about this is the derivative with respect to x of y times the derivative with respect to t of x. Right? That's written here in Leibniz notation, which is really the nice, compact, and feel-good way to write the chain rule, because we're taking the derivative with respect to y of t, and we can write that as the product of the derivative of y with respect to x times the derivative of x with respect to t, and our little inner brain starts to feel really happy because it's like, hey, let's cancel those out. But remember, these aren't fractions; you can't cancel them out. But it feels good to write it like that. Let's now go on to our functions of several variables. So let's say we have z is equal to f of xy, where x is a function of t and y is a function of t. So we have z is equal to a function of g of t comma h of t. And so what we might want to do is we might want to know what is dz dt. Right? And in this case, it's dz and not del z, right? Because this is only a function of t and not a function of two variables. And so what does the chain rule give? So the chain rule here is going to give dz dt is the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. So if we wanted to write that out in the similar way to what we had before, is you take the partial with respect to x and you plug in your g and h, and you multiply by the derivative of x with respect to t. Then you add into that the derivative of y with respect of f with respect to y of g and h, and then you multiply by h primed. So what's the takeaway message? What the takeaway message is, z was dependent on x and y, and x was dependent on t, and y was dependent on t. So all the ways in which z is changing that depend on t go through both x and y. So you have to add the contributions from all the dependencies. All right, so let's look at this one. If z is equal to x squared y plus 3xy squared, x is equal to sine of 2t, y is equal to cosine of t. If we wanted to find dz dt, then what we do is we say, okay, so dz dt is equal to dz del z del x times dx dt plus del z del y times dy dt. So in this case, del z del x is equal to 2xy plus 3y squared. Dx dt is 2 sine of 2t. and then we have to add in del z del y, x squared plus 6xy times the derivative of cosine, negative sine of t. And then we need to plug in for x and y as functions of t. And so what we're going to get is something really long, really ugly, which is 2 sine 2t cosine t plus 3 cosine squared t times 2 sine 2t plus sine 2t plus 6 sine 2t cosine t times negative sine of t. So it's a one long expression, and if you think about it, this answer right here, let me highlight it. This answer right here the joys of technology. All right, this answer right here this answer right here, it's not good enough as an answer to what is dz dt. All right, so the reason why it's not good enough is that here z is really a function of t, and so the answer shouldn't have any t's, shouldn't have any x's and y's in it. It should only have t's. All right, so let's look at a more complicated example. So we might have a function where z is equal to a function of x and y. X is a function of two variables, s and t. Y is a function of two variables. So when we're doing this, when we want to figure out the derivative of z with respect to s, we have to find all different ways in which z is related to s. And so what I find really helpful is for us to draw a picture which says, okay, z depends on x and y, and x depends on s and t, and y depends on s and t. And so what we need to do is we need to find all ways that z is dependent on s. So here's a chart, a tree, that tells us that in order to calculate how z is changing with respect to s, well, we need to go through x and we need to go through y. So we get that del z del s is del z del x times del x del s plus del z del y times del y del s. All right, sometimes we get an even more complicated example. So we have u that's dependent on x, y, and z, and x is dependent on r, s, and t. So if we want to find del u del s, then we need to find all ways in which u is related to s. Right, and so what that means is we'll have to write that del u del s is equal to del u del x times del x del s plus del u del y times del y del s plus del z u del z times del z del s. And so you can go through and you can calculate each of these bits, and each of those bits then contributes to the ways in which u changes with respect to s. And so if we want to be completely general, we can say, let's say u is a function of these variables, x1, x2, up to xn. And then each of the x sub i's is a function of some t variables. Then del u del ti, right, this is what is this going to look like? This is going to look like u, x1, x2, x3, dot, 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 xn. And then each of these has t1, ti, up to tm. And so in order to get all the different ways that the variable u is dependent on ti, you have to do del u ti through x1, del u through to ti through x2. So del u del x1 times del x1 del ti plus del u del x2 times del x2 del ti. And you do that for all different ways that you can do this. All right, so let's stop there.